Okay, so we are going to graph our first set of data following the rules that we'll use for every graph in class. Rules that are on this sheet, rules for graphing, which if you ever misplace it, you may also find a blank copy on the class website in chapter 1 stuff. But we're just going today to go down the list, one item at another, answer any of the questions that are posed there, and then translate that onto our graph. So number 1 here, it says identify the dependent and independent variables for the data set. We, of course, did that as part of our setup. The independent variable for our first rocket launches was how much water we put in the engine. And the dependent for all of our rocket launches is going to be how far it flies. Sometimes that would be undefined for you. So if you got a description of an experiment, you might have to do that yourselves. Always read the instructions or the description and determine which of those does the experimenter have most direct control over. That will be the independent variable. Okay, for us, we're going to now go on to number 2, draw axes near 2 edges of the graph paper. Rotate, please, your graph paper. We're going to do this the wide way. It doesn't have to be done the wide way, but we want to use as much of the paper as possible. Yeah, you'd start a new page because we want it to be nice and big. That makes the graph easier to see. We're going to draw 2 axes. What are axes?
X and Y. The main positive. The line where if you go above it is positive and then you go below it.
I heard a lot of people say X and Y, and they're the lines that divide the graph. Right. So go up, let's say 4 or 5, probably 5 graph squares in from the left and 5 graph squares up from the bottom for your line, because we're going to need room around them to write values and labels and things. I'm actually, because I know this is going to take up most of my graph, I'm going to, and I have a margin on here, I'm going to use the edge of mine. But since you don't have that on yours most of the time, count in 5 squares. Oh, notice that I'm using a ruler. Please also always use a ruler.
Should we go up like how many squares?
What's that?
How many squares up?
About 5 squares up, 5 squares in. I have plenty of rulers to share, so always grab a ruler when you're going to make the graph.
Oh, just nailed me funny.
Okay, and then I'm going to go along the bottom, do the same thing, just count up 5 squares and draw your line. Next, guys, label the x-axis. Which one's the x? Bottom one is the x. With the name of the independent variable with its units in parentheses. Independent variable in a graph always goes along the bottom. That's the one you changed directly. So for us, that was engine water. I'm going to leave the space right by my axis blank and go down a couple squares because that's where we'll put values. And then in parentheses, we always have to put the units. Unless it's something that we're just purely counting, like a number of donuts. We are always going to put the units that these are measured in. So milliliters is little m, capital L.
Is it okay if you wrote it out?
What's that?
So if you actually wrote milliliters?
Yeah, that's fine too. Now on to number 4. Scale the x-axis. This means determine how big the squares are. So the minimum value in your data is near the left-hand side and the maximum value is near the right-hand side. Mark off the scale along the axis with tick marks and values. And really, really importantly, all squares must represent the same number of units in the x direction. We're missing some of our data over here, so we skip some of them. We cannot skip them on that graph. We won't have any data above them, but we can't just ignore them altogether. So we go from 0 and we go down a little bit to 2,000. We'll need 0 to 2,000 on our axis. So a good idea is count how many squares you have available, and then we'll determine what a convenient scaling will be. So I've got I have just over 40, and I go from 0 to 2,000. So that means each square, I could skip a square, and every other square would be 100. So each square ends up being 50 millimeters. What's that?
So they do it.
Have to go to 2,000 because our data here goes to 2,000. So 0 to 2,000 for this. The way mine fits, I'm going to start at 0, of course, on the left-hand side, and everyone should. I have enough room to skip every other one, and that'd be 100. Here's 200. I don't have to label every square because that would get really crowded. So it's okay to skip one, or as long as you're really consistent.
Wait, these rulers to make the little.
No, you don't. Little tick marks you can just make, and if you've got room, you can do it the exact same way. If you find that you're a little squished, you might go every other one is 200. But we'd like to take up as much room as possible with this. So I'm going to label these. We don't have to worry about units because we already put them along with the title at the bottom.
I skipped one that I'm on to have.
What's that?
I skipped like a box or whatever every time, and I'm on it to half the page, so it's gonna make it bigger.
Should make it bigger, yep.
I was mine. I can go to 1,000 easily, but if I try skipping something, should
Yep.
I just do the 100?
We have to make it fit. So whatever that works out for yours, it could be a little different than mine. Okay, now we've got our x-axis marked. Going back to our rules here, number 5 says label the y-axis with the name of the dependent variable and the units it's measured in parentheses. So same sort of thing, but now we're doing this vertical axis. This is what you measure. So for us, that was flight distance. Remember to leave some room for labeling here, the numbers, and then I'm going to write flight distance up here, and then the units we measured that in were meters. Number 5, label the y-axis with, 6, scale the y-axis so the minimum value in your data is near the bottom. The maximum value is near the top. Mark off the scale along the axis with tick marks and values. And just like before, all squares must represent the same number of units in the y direction. But they don't have to be the same as what we just did here on the x.
How about like 20?
Well, let's see. We want to find our minimum and maximum. So we start, our minimum is 9. Our maximum in this data is 110. So we have to accommodate that at least. I'm going to count the squares again. I have 38 squares up that way. You will find, since you are doing it sideways, you have fewer squares to work with. So I have 38 squares. I'm just going to make a note of that up here. I'm going from 9 to 110. And I can certainly, again, start at 0 here if that's convenient for me. I, again, want to pick a number here that is convenient. So if I did something like 2.2, I could count that up and keep adding, but it would not be very convenient. It's easier to use a whole number whenever possible, and one that you know all the multiples of. I could probably go by 3 per square. So that'd be 3, 6, 9. I think that would work. But that's kind of a weird one to keep adding up. So mine, what mine will probably fit is that I could do 10 every 3 squares. You guys will probably find you want to do it a little differently. Maybe you go by 10 every 2 squares, so each square is 5.
We have to go up to what number?
We have to go up to 110. Let's do this a little more consistently, since I think it'll fit better on yours. I'll do every other by 10. Mark every, so each square is 5 meters. You should be able to fit that out, I would think, on yours as well. So we'll just keep it consistent.
So there's like 33.
And I know I want a little bit of room around the top for title and stuff too, so this will give me that. So I could use more of my graph, but for this one I really don't need to. Go up to 1. Next step, number 7, title your graph with a name that describes what it's showing. The title should be prominent and centered above the graph. So I'm going to write it up here. A title is not My Rocket by Little Timmy. For graphs, the title has to describe a little bit about your experiment so that the reader could know what you are experimenting, at least in a general way, based just on the title. So for ours, since we were testing the flight distance of water rockets compared to how much water we had in the engine, we can condense that a little, but it should include those points. So I'm going to say flight distance of water rocket and then the word we use to, instead of compared to, is very often versus, and we often also just write the abbreviation, either a VS or a V. The versus engine water, volume or engine water.
You engine water, bro?
Yep. Any of those are fine. Number 8, plot your data with darkened spots. Don't connect these, by the way. We really won't just draw dots and then connect any of them in this class, but we will almost always use this type of graph, which you could call an XY scatter graph. where you just plot the points, and then we're going to draw a curve through them, but not point to point. So I'm going to start over here. Don't have any data above 200 or 400, or 0 or 200. For 400, I should go up to the 35 mark. So find my 400 here, go up to the 35 mark, take across. So I'm going across from the left, up from the side, put a dot there. 600, we have two pieces of data, 89 and 93. So since not all of these will be on the lines, I'm going to estimate as closely as I can where they would fall. Oh, that's 79. 89, 93. And we just, since there are 2 points of data there, we just put them one above the other. No data for 800, 1000 is 54. We've got 1200 is 88. Yeah, this is being recorded. Okay, now after we've plotted these, we want to connect our data with a smooth best fit curve. If the data is basically in a line, the best fit curve will be a straight line that passes through the average value of your data and to show the trend. We'll practice one of those probably tomorrow. In that case, if you've got a line, use your ruler again. These curves or the lines are not going point to point, they're just showing an estimated average. A computer can do this very, very well. Your calculator can do it very well. We are going to use our own human intuition to try it. No, they aren't, but I'll show you what I mean. Now, the second point here, if your data is arranged in a curve, and this one definitely goes up, it peaks somewhere in the center, draw a smooth arc through it, so some points lie above the arc and some points lie below. Again, this arc should show the trend of the data and should not be drawn from point to point. So I see this, we start out pretty low down here. If we had had a 0 or a 200, we'd probably even be lower, it looks like. We peak somewhere in this range, and then we trail off. Now we had a particularly good rocket there, not as good a rocket here, but we can kind of see the curve even with those kind of outliers. And that's why this best fit curve is nice, because sometimes our experiment goes really, really well and sometimes not quite so well, but this is showing the trend of all of them together. So what I'm going to do is I'm going to start down here in the lower left. Don't have to go to 0. In fact, I shouldn't, because if I had zero water in my rocket, I'd still have compressed air, so I would expect it to fly some distance. I don't know exactly how far, we didn't measure that one, but it wouldn't be 0. It would come off the launcher.
For the, in between the 1600 and the 1400 or whatever, how come there's that big a difference if it's only like 200 things?
I expect this was our best rocket. I think it was just built the best. I don't remember whose it was. But fins make a can make a big difference. Now, if we take that same rocket and test all of these, we'd get an even clearer view of how the engine water affects things. We tried to make every rocket the same, but we didn't. We can't. I mean, different people are doing it differently. So that's probably why we have one up here. Now this one, maybe the fins weren't so good. I don't know. I don't recall. So that can make a big difference. And that's a weakness, but it's not that bad. So I'm going to start down here somewhere, and I'm going to draw a curve that goes kind of amongst all of these, and it'll dip back down over there. Like so. That's not very dark. I'll try and retrace that.
Start at like 30.
Yeah, I started around 30. We can't predict too well what it would do before that without data. Okay, but that is our best fit curve. Now we can see, although we had a really, really good one here at 1400, if we use all of the data, that says our best bet would be, at least in my curve, somewhere around here. Following that down, that's around 1100 or so. And then that would be our suggestion of a very good amount to try for our next rocket.